5.4, logarithmic functions. Today we're going to be getting a brief review of going from exponential to logarithmic and logarithmic to exponential, and using that knowledge to make graphs, to solve equations. We're going to have a lot of work that we're going to have to do in this one. But these first two examples are very, very important, especially example 2. So, quick review, going from log to exponential. Here's logarithmic form, log base b of x equals y. And then we have b to the y equals x is exponential. To go from here to here and vice versa is what we're going to be doing in the first part of this section. It's a algorithm that you need to follow. If it is not followed correctly, you will not get anything correct throughout this section and the questions from your quiz and your test. So please make sure that we definitely try to understand how to go from exponential to logarithmic and logarithmic to exponential. If you need to watch it again, if you need to come in for help, or just remember to ask me in class tomorrow when we're going over this section. So, in example 1, we're given functions in exponential form. This is b to the y equals x. So I'm going to start by identifying my variables. B is 5, y is 2, x is 25. Now I just need to plug into log form. And log form is log base b of x equals y. So log, what was b? 5. What was x? 25. What was y? 2. So there's log form. I'm not going to go over that method for every single one of these. I'm just going to identify my variables. B, y, x. So log base b of x equals y, and this is something we're going to make sure we have to have memorized. B is a, x is 1.6, and y is 2. Now, c is a little bit different. So I have b, I have y, I have x. So this is log base e of m equals 2.2. Some of you might remember from last year, though, who took the honors course, we learn a second logarithmic function. And those of you in the regular math 3, I think you barely touch on this, if I remember correctly. But e goes with ln, the natural log. So I could actually use the natural log here instead of log. So that one is fine. But I might decide that, oh, I see an e and I want to get rid of e. I need to get rid of e, so it's not an exponential form anymore. So in order to get rid of e, I natural log both sides. What I do to one side, I must do to the other. So I natural log to get rid of the e. So I have 2.2 equals the natural log of m. So I'm not in exponential form anymore, and I've written this as a log. So this is the way that I would like to see you do this, starting to get that understanding that e and ln, the natural log, go together, and that they undo each other because they are inverses. Just like logarithmic functions and exponential functions are inverses, which we will be seeing as we continue through this section. Example 2, we are going to have functions in logarithmic form that we are now going to want to write in exponential. And these should make sense. If this doesn't make sense, if your equation doesn't work, you did something wrong. So b, x, y. And this is b to the y equals x. And if you're used to b to the x equals y, that is fine. Also, you can switch the variables. Not a big deal, as long as you label everything appropriately. The base of the log is the base of your exponential form. The solution of the log is your exponent. So 2 and it equals 16. What I mean by this not making sense, if you had written this as Maybe 2 to the 16 equals 4. That does not make sense. Maybe you wrote this as 16 squared equals 4. Doesn't make sense. So you want to make sure that when you are finished, your exponential function makes sense. Now in B, you do have a variable, but it's still very easy. Your base, your exponent. So 3 to the x, and what must that equal? 2. Now we're not solving for x, we're just rewriting. Here, 5 is your base, negative 2 is your exponent, and does it make sense that you would get 1 over 25? Yes, because you have a negative exponent, which turns the 5 into a fraction, and 5 squared is 25. Let's move along to example 3. Find the exact value without using a calculator. So in 5.3, we went over how to solve an exponential function. So I want to rewrite this as an exponential function. So I'm going to set this equal to a variable. You could pick x, you could pick y, you could pick r, whatever variable you want to use. Just remember, this is your base, and what it equals is your exponent. So this is 2 to the y equals 16. Now in 5.3, we had to rewrite 16 so it would have a different base. You cannot solve for an exponent unless your base is equal. So 16 becomes 2 to the 4th. So I have 2 to the y equals 2 to the 4th. You can ignore your bases, so y equals 4. I'm going to do that again in B. This time I'll set it equal to x, so you guys can see it doesn't matter what the variable is that you write, just as long as you're solving for it. So 3 is my base, x is my exponent. 1 over 127. Sorry, 1 over 27. Well, that's a fraction. And what did a fraction used to have? It used to have a negative exponent. So I can rewrite this as 3 to the x equals 27 to the negative 1. Now I need to remember that 27 can be rewritten as 3 cubed. I'm not teaching you all this multiplication stuff here, you guys. This is the stuff that I expect you to be able to do. So I have 3 to the x equals 3 cubed, and I bring down the negative 1 that was originally here. Bases are the same. X equals negative 3. Shouldn't be too bad because you should have practiced this in 5.3's classwork. Moving on. Now we're going to start looking at the logarithmic function in preparations for graphing and understanding the pieces of a logarithmic function. And logarithmic functions, they represent, like in the real world, they would represent something that starts growing really fast and then maybe grows slower and slower and slower over time. And we did do some examples like that in Math 3 last year. So finding the domain, one of the things we need to remember with logarithmic functions, when you rewrite them in exponential form, so this would be b to the y equals x. If I make y equal to 0, so let's say b to the 0, what would that give us? 1. There is nothing that I could plug in. Say I plug in negative 1. Well, that's 1 over b. B will never be 0. Your base can never be 0 because you'd go nowhere. You'd be stuck at 0. B will not be 0. Because B will not be 0, x will never equal 0. Or can never equal 0 because there's no exponent that exists that will ever give us 0 other than 0. And again, we would be stuck with 0. So when I'm looking for my domain, I need to remember the part that is with the log, the x, has to be greater than 0. So we're looking at a third function now where the domain is not negative infinity to infinity. Just like when we had a fraction, we set the denominator equal to 0 and we solved for x. And that's what x couldn't equal because that would be undefined. A square root, we set that greater than or equal to 0 because we cannot square root negative numbers. That would give us an imaginary number, which would not be in our domain. With logarithmic functions, because we will never ever be able to get 0 unless there's some transformations taking place. We have to double check that what we are taking the log of is never going to be 0. So I take x squared, the main part of the log, and I set it greater to 0. Greater than 0. So x has to be something to 0 because I would square root this. Whoa. I would square root this and I would get plus or minus 0. Well, I am not sure if this has to be greater than 0 or less than 0 because of that whole squaring process. So the part that you guys dislike the most is the testing of values, but that's what you have to do here. So the 0 gets an open circle because it has to be greater than 0. X cannot be 0. And I test -1 and I test 1. So I plug this back in. It has to be, x squared has to be greater than 0. So -1 squared is 1. Is 1 greater than 0? Yes. So I highlight that piece. Now I plug in 1. 1 squared, is that greater than 0? Yes. Now I highlight that piece. Now we have to remember to write our solutions here, and that was something that you guys have been struggling with this year, is remembering to write the solutions. So my solution, the left side is -infinity to 0, not included, and then from 0 to infinity. Now let's look at this next one. Here is the main part of your log. So 1 plus x and 1 minus x, this cannot equal 0, and it can't be less than 0 either. So let's just find what makes it 0 first. We start with the numerator, so now we got to remember from the exponential functions. If I look at the numerator, 1 plus x equals 0, x would equal -1. But you also have to look at the denominator because you cannot have a 0 in the denominator. So 1 minus x cannot equal 0. So I move the x over and x equals +1. So on my number line, I would have -1 and 1. Both would have open circles. Everything with logs is going to have open circles. So I have 3 numbers I need to test: -2, 0, and 2. So I'm going to go through this work, and I have to plug into the 1 plus x over 1 minus x, and it has to be greater than 0. So 1 plus -2 over 1 minus -2 must be greater than 0. 1 minus 2 is -1. 1 minus -2 is 3. Is that greater than 0? No. So that piece does not work. Now I plug in 0. 1 plus 0 over 1 minus 0 has to be greater than 0. So 1 plus 0 is 1. 1 minus 0 is 1. Is that greater than 0? Yes. So that piece works. And then the last piece, 2 plus, sorry, I keep putting the wrong one first. 1 plus 2 over 1 minus 2 must also be greater than 0. 3 over -1, is that greater than 0? No. So now I need to write my solution. It's between -1 and 1, not included because they are open circles. All right, now let's move on to the graphs. I think this is where we wrap it up, and I'm not going to go over everything here. And then we have example 6. Okay, so in Math 3, you have graphed logarithmic functions. How you were taught this is going to vary depending upon which teacher you had. I'm going to teach this how I taught my Math 3 students. It's going to look a little different than what is in your notes. These notes were done a few years ago before we had this new curriculum that we are using now. So the background of the logs and the graphing wasn't quite as extensive as what you have had. So I am going to go over this as knowing that you have seen this before, and I'm also going to use the way that we are taught in Math 3. So you might want to write this down as I am going. The first thing I'm going to recognize is that I do have a log, and I want to make sure that I rewrite this in exponential form because I don't know how to graph a log, but I do know how to graph an exponential function. We did that in the last section. So this becomes 2 to the y equals x. So when I plug in my values, when we make a table, we make it x, y. When I look here, I see that my exponent, though, is y. Since this is my exponent, those are the numbers I'm going to pick for first. I'm going to pick -2, -1, 0, 1, and 2. So 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the 2 is 4. Those are the points that I'm going to plot, and I'm going to have my graph. So I'm not going to have to go through the entire process of creating the exponential graph using the inverse function. I'm going to just graph these points. Now, why does it say there is a vertical asymptote at 0? We need to remember from the previous example, this cannot be 0. So I have to put a vertical asymptote here. So that way I remember my graph cannot cross that axis. Now let's plot some points. X was 1/4 when I plugged in -2. So 1/4, -2. X was 1/2 when I plugged in -1. X was 1 when I plugged in 0. X was 2 when I plugged in 1. And X was 4 when I plugged in 2. And now I can see my graph. There is a logarithmic function graphed. Now let's do this in the next one. Again, I'm going to rewrite this into exponential form. So this is 1/3 to the y equals x. I'm going to make this a little bit easier for me because I don't want to deal with the fraction. So remember, fractions come from negative exponents. So this is 3 to the -1 y equals x. So now I'm going to make my table, x and y. And don't forget, we're picking for y because that's our exponent, -2, -1, 0, 1, and 2. So when I plug in -2, this is 3, -1 times -2. Well, that's +2, and 3 squared is 9. Now I'm going to plug in -1. -1 times -1 is +1, and 3 to the 1 is 3. Now I'm going to plug in 0. 3 to the -1 times 0. Well, that's 3 to the 0, which is 1. Now I'm going to plug in 1. 3 to the -1 times 1. That's 1/3. And 3 to the -1 times 2. That's 1/9. So now I got to plot these points, and I have to put in my asymptote again because I need to remember you cannot cross the x-axis unless there's a shift, and there isn't a shift here. There's no left or right movement. I would know that if there was a value with the x. So now I just need to plot these points. When x was 9, y was -2. Way out here, I'm not going to graph that. Let's see if I can figure out this graph without that. When x is 3, y is -1. When x is 1, y is 0. When x is 1/3, y is 1. When x is 1/9, y is 2. And you can see it's getting really close to the the y-axis, but it's not going to touch because of that asymptote. Sorry, I missed those points, but rough sketches is all we're looking for, or I'm looking for. All right, moving on. So now I see a graph that is going to have a shift. Because there's this +1, that means my graph is going to go left 1. So my asymptote, please watch, my asymptote would normally be at x equals 0. But since I am moving, oh, I don't want the whole coordinate plane. Since I am moving, oh, man. Since I am moving left 1, just pretend those things moved with it. I don't know why it's not working. Let's see if this will work. Okay. I'm going to move these left 1. There's my new vertical asymptote. So I can ignore the x plus 1 now. What is the base? 3. So if I rewrite this in exponential form, this is 3 to the y equals x. F of x is the same as y. So now I don't have to worry about the left 1. Not yet. I will in a minute. I'm going to plot these points first. So remember x and y, and we plug in -2, -1, 0, 1, and 2. 3 to the -2, 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. So I plot these points. I'm going to plot these very lightly because I still will have to move them left 1. So 1/9, -2. 1/3, -1, 0, 1, 3, 1, and then 9, 2. And I'm not going to plot that one. Now let's move all of these points. I'm going to use green for this. Let's move all of these points left 1. And I'm going to connect the green dots. And there's my graph. I'm not worried about you guys graphing the next one, so I'm going to just leave that one the way it is in your notes. If you get it, you get it. If you don't, you don't. I'm not worried about that one. In this next piece, this is just understanding E and ln are inverses of each other, and their graphs are going to look just like the exponential and the natural log. But I'm not really worried about you guys going through and graphing the exponential first. Know that this is the natural log graph. Use this here to save you some time. It looks a lot like the logarithmic graph. I just used the ln button on my calculator. I took the ln of 0, the ln of 1, the ln of 2, the ln of 3, ln of 4. And when I took the ln of 0, it gave me a math error. Well, that's my asymptote. When I took the ln of 1, I got 0. ln of 2, it looks like it's between 1 and 2. When I took the ln of 3, it looks like maybe it's almost 1. So table of values if you want to. And then in here I just took that graph and I moved it left 4. I'm not going to go over the domain and the range. You guys should be good with that. The asymptote, you should be good. The inverse, I'm not too concerned about. Let me talk you through it. So here's my original function. Inverse means switching x and y. So once I have x and y switched, I need to get y by itself. To get rid of ln, you have to e both sides. So the ln and the e cancels, and I'm left with e to the x. E is exponential. It's e to the something. And x is that something, then I subtract 4. So there's my exponential function. And then you guys would just need to create the graph of that function. And e to the x is a growth, an exponential growth, and the -4 says move it down 4. If you get it, great. If not, that's fine. I want to move on to example 6. So solving a logarithmic function. It's really hard to solve a logarithmic function if you don't switch it into exponential form, which is why examples 1 and 2 were so important. We have to notice that, oh my gosh, I have 1 log. I need to rewrite this. So this becomes 3 to the 2nd equals x, so x equals 9. So much easier if you guys rewrite this into exponential form. My base is 4, my exponent is 3, equals x plus 7, x to the 3rd. 4 times 4 is 16, times 4 is 64. And then I would subtract my 7, and I get 57. And then in the last one, x to the second equals 1 over 25. So now we need to kind of think about, okay, I have a fraction. It might make things a little bit easier if we go ahead and solve for x by switching that fraction, and that's fine. X squared would equal 25 to the negative 1. I don't know if that's going to help us much at all, but because I have a fraction, I need to be thinking that, oh, fraction, negative exponent. But if I look at my exponent, it's not negative. So I'm not going to think of it this way. I'm going to think that x must have already been a fraction. So I'm going to kind of work backwards. And I'm going to think, well, what squared is 25? Well, 5 squared is 25. But if I don't have a negative exponent, how did it become a fraction? It was already a fraction. 1/5 squared is 1 over 25. So what does x equal? 1/5. So it is okay to go ahead and use backwards thinking here and kind of figure out, well, if this is what I have, what must I have needed to get there to make this a little bit easier for you. If it was a negative exponent, then it would have actually been 5, not 1/5. So not too bad. That was it for 5.4. If you had questions, hopefully you wrote them down, or go back and find where you had those questions and write them down and ask me in class tomorrow, or when you get in class, just get started on your classwork.